Uh, Welcome to another BIMSA member seminar. It's pleasure to have Professor Sze-Man Ngai, who is going to talk about the multifractal LQ spectrum and beyond.
Thank you. Thank you for the introduction. And I actually would like to first thank the member seminar committee for their hard work. The word fractal was coined by Mandelbrot. It does not have a rigorous mathematical definition, but for different classes of fractals that we're going to see, there are rigorous mathematical definitions. Right? So fractals is used to refer to sets that possess some, not always all, of the following properties: infinite complexity, self-similarity, and non-integral house of dimension. And I'll explain first house of dimension, the definition of house of dimension. Let's start with the house of measure. Okay. The house of measure is an extension of Lebesgue measure. So let S be greater than or equal to 0, E be a subset of Rn, then house of measure HSE is defined as follows. First, you take a countable cover of E, countable cover of E, each of which has diameter less than or equal to delta. And take the diameter raised to the power S and take the sum. Now, and then take the inf. Take the inf. This is a monotone increasing function. As delta tends to 0, you get a smaller set here. So let delta tend to 0. This is the definition of house of measure, S-dimensional house of measure. If you change S to N, then this is a multiple of Lebesgue measure. So if you take any set in Rn and compute its house of measure, then it always behaves like this. It's either infinite or 0, or at most at one point it could be finite and positive. So the house of measure of E will drop from infinity to 0. At a single number, and this number is called the house of dimension of E. So this is the definition: is the inf of all S such that Hs is equal to 0. It's equal to the sup of S such that HSE is infinite. So here's the significance of house of dimension. It determines a unique house of measure Hs that can be used to measure the set E meaningfully. That means it's the unique house of measure that could possibly give a positive and finite value for the set E. Right. So let me give you an example of a fractal set. So this is called the Sierpinski gasket. Start with an equilateral triangle, divide into 4 equal pieces, keep these 3 and remove the middle one. And then iterate this process. So for each of these triangles, remove the middle inverted triangle, and so on and so forth. Now, this will give us a decreasing sequence of compact sets, non-empty compact sets. So we know that the intersection, this is the intersection of, this is the intersection of the sequence of compact sets. This intersection is called the Sierpinski gasket. So it's self-similar in the sense that if you take a suitable copy like this, it's similar to the entire. You can take smaller, very small, suitable copy, small subset, suitable subset, and similar to itself, to the whole entire set. So this is called self-similar. This is notion of self-similarity, and it's also it has an infinite irregularity. Okay, so it won't get smoother as we magnify the set, magnify any point. Okay, so it looks the same no matter how much you zoom in the set. Okay, it turns out that the Hausdorff dimension of this is a fractional number 1.58. So there's a method to compute the Hausdorff dimension, but I'm not going to mention it now. Okay. So this is one way of constructing the Sierpinski gasket. There's another way is to use a finite set of contractions, mappings. Okay. So this is the another mathematical way of describing the construction. So start again with the equilateral triangle and apply three maps. Okay, S1. Okay, so S1 is just a contraction plus possibly a translation. S2, S3. So each of these maps shrinks the triangle by a factor of 1/2, and then translate the shrunk copies so that we get this this set F1. Okay, and then you iterate this process. You apply this maps. Okay, compose these maps. Say S2, S1 is this, S3, S3 is this. Okay, so this way we can also describe the attractor, this limit. Okay, I'll define the attractor in a moment. Okay, and so this collection of sets is called an iterated function system. Okay, of contractions, and to each iterated function system there is a unique invariant set. Okay, so I'll define in a moment. Okay. Now,
Naive question.
sure.
So is there connections between Hausdorff dimension and fractal dimension?
Fractal dimension.
Yeah.
The fractal dimension is, I think it's a general term. There are several notions of dimension. Hausdorff dimension is probably one of the most useful ones, and there's box dimension, and which could be different from Hausdorff dimension. So I think when you say fractal dimension, it's probably refers to Hausdorff dimension, but it could also refer to box dimension.
I see. Okay.
I want to also explain that to each iterated function system, like the system of maps, there exists a unique probability measure, okay, that is invariant. So how to get a probability measure? So for S1, we will assign a weight P1, say P1 to this triangle. For S2, assign the weight P2 to this triangle. S3, we apply P3 to this triangle. Okay, and you use the same process. P1, P2, P3 are, say, positive, and they sum up to 1. So for S3, S3, the way to apply is P3, P3. So S2, S1, the weight we apply is P2, P1. Okay, so the sum of these weights always add up to 1. Okay, so, and in the limit, we will get a measure supported on the set F. Okay, that's called an invariant measure. That's in my next slide. So this is kind of a little bit more technical. It just says that given any set of contractions called an iterated function system, there exists a unique non-empty compact set called the attractor. Okay, the attractor here called F is the union of the copies of F under the maps. Okay, so in the Sierpinski gasket, F is the union of 3 copies. Okay, and as I explained, there is a unique measure. Okay, measure called the invariant measure, satisfying such an inequality. Okay, and the construction of measure is, what I just explained. Okay, so for each composition of map, you assign a weights according to the composition. Okay, so if the SI, the maps are contractive similitudes, so these are maps of the form SI equal to RI times the rotation or orthogonal transformation. Lowercase RI are called the contraction ratios. The numbers between 0 and 1. RI is orthogonal, and BI is a translation. So such map is called a similitude. And if the maps SI are similitudes, then the corresponding attractor is called a self-similar set. And the corresponding measure is called a self-similar measure. So fractal measures are usually very irregular, highly irregular. So here is an example. I use the Cantor measure. Cantor measure can be defined by an iterated function system of just two maps. Okay, one is contraction by 1/3, the other one is contraction by 1/3, and then translate by 2/3. Okay, and we can put a weight P1, say 1/4, P2 equal to 3/4. They sum up to 1, and the density plot is highly irregular. Okay, so to describe this irregularity.
Excuse me, what is P in the what is P here?
Are you referring to this P1? Oh, these are probability weights to generate the measure. So to describe this irregularity, so it defines the multifractal component with local dimension alpha. Okay, so we take points in the support, okay, so that this quantity, which is log of the measure of delta bar divided by log delta, equal to alpha. So this roughly says that the measure of a delta bar is approximately delta to the alpha. Okay, so for different points, we could get different values, okay, of these local dimension, or yeah. So the question is, well, this is a component of the support, okay, a subset of the support, okay. So how to compute this, the house of dimension of such a component, okay. So this for different alpha, we get a value, which is a dimension of the component, okay. And so this function is called the dimension spectrum. So physicists first proposed a way to compute this, to compute the dimension spectrum, okay. So this is mathematical formulation. Is not entirely the same as what they proposed, but roughly the same, okay. So the idea is to compute the LQ spectrum. This is in the title of my talk, okay. So the LQ spectrum is obtained by taking the qth power of the mu measure of a delta bar, and then you take the sum. Now these bars are disjoint, okay. Delta bars with center in the support. Okay. Take the sum and then take the sup over all the possible families of disjoint delta bars, okay. And take the logarithm divided by log delta. So this roughly measures how this sum behaves as delta tends to 0, the exponent of the sum, okay, delta to the power of, okay. So this is the LQ spectrum, and physicists propose if you take the Legendre transform of this LQ spectrum, defined as the inf of Q alpha minus tau Q, then the heuristic multifractal formalism says that tau star alpha, the Legendre transform of tau Q is f of alpha. Okay, so it's a heuristic formalism. Okay, so here's the example of the LQ spectrum for the weighted Cantor measure that I mentioned, typically it's a concave curve like this. Okay, and this is the Legendre transform, also concave. And if you take an alpha here, tau star alpha tells us the Hausdorff dimension of the set, the subset of the support with local dimension alpha. The multifractal formalism has been proved rigorously by Colley and Malden for self-similar measures that satisfy the so-called open set condition. Okay, so it says the open set condition says there exists a bounded non-empty open set U that is invariant under Si and satisfies the separation condition SIU in the SJU is empty. Okay, so the Chebyshev gasket is defined by an iterative function system that satisfies the open set condition. Let me go back. Okay. So if you take the interior of this triangle, it's an open set and it's mapped by S1, S2, S3 into itself. Okay, and these three subsets are disjoint. Okay. Now, without the open set condition, the problem becomes. Oh, sorry, I've before. I want to say a little bit about the general properties of the alkyl spectrum. Okay, so it's typically increasing concave. It's when Q equal to 0, it gives us the upper box dimension of the mesh. Okay, which I'll define in the next slide. Tau of 1 is always equal to 0, and its derivative, okay, at 1 is the Hausdorff dimension of mesh, which I will define in the next page. Okay. This is asymptotic slope. Okay, is called the L infinity dimension, okay, or lower L infinity dimension. Okay. All right, so here's a summary of the figure. Increasing concave, tau 1 equal to 0, and it's resolved by Parison-Solomyak. For class of measures that include the self-similar measures, the limit defining tau 2 exists for Q greater than or equal to 0. Okay, tau 0 is the box dimension as box counting. So we can define it as the limit of n delta f over log delta. N delta is the minimum number of closed bars required to cover f. Okay, so this is usually the box dimension is easier to compute, okay, than Hausdorff dimension, but not always. Sometimes it's just as hard. And myself and Erder proved that if tau is differentiable at Q equal to 1, then tau 1 is equal to the Hausdorff dimension of the mesh, okay, which is.
This also does not require any open set.
No, this does not require any open set condition, and it's for all measures. Okay, so it's inf of the Hausdorff dimension of E such that mu of Rn, actually Rn minus E equal to 0. Okay, it's the Hausdorff dimension of measure, and this quantity called the lower L infinite dimension will also appear in study of the analysis of Laplacians associated with the mesh. Okay, so iterative function systems that do not satisfy the open set condition are said to have overlaps. Okay, so a family of examples of iterative function systems that do not satisfy open set condition is obtained by picking just two maps. Okay, two maps. One has both have contraction ratios equal to R, same contraction ratio, and we take the equal probability weights, 1/2, 1/2. That's probably the simplest system, but it's not simple. This is classically called the infinite Bernoulli convolution because it's associated with infinite convolutions of Bernoulli measures. Okay, this problem actually was studied since 1930s. Okay, Erdős proved that the corresponding measure mu r is singular if the reciprocal of r is a Poisson number. Okay. A Poisson number is an algebraic integer greater than 1, all of whose algebraic conjugates are in modulus less than 1. Okay. Solomyak proved that for almost all r in the interval 1/2 to 1, mu r is absolutely continuous with respect to the back measure. If r is less than 1/2, then it's simple. It satisfies the open set condition, measures singular. Okay, and some landmark results have been obtained by Perez, Schlag, Hoffman, Schmerken, and Vajou concerning the exceptional set, the size of the exceptional set. But it's still open for which r in this interval is mu r absolutely continuous. Okay, still actively researched area. Concerning iterative function systems with overlaps, well, there are lots of results, but I'll just mention this result concerning the Bernoulli convolutions. Okay, so for the infinite Bernoulli convolution associated with golden ratio, okay, golden ratio is square root 5 plus 1 over 2 is a Poisson number. Okay, so this is a reciprocal of the golden ratio. If you take r equal to the reciprocal of golden ratio, then you can compute tau q. Tau q is given by a formula like this. Okay, where Cj, I've not defined it. Cj is the weights of small intervals. Okay, measure of small intervals. Okay, it's given by this formula, and using this formula, you can show that tau q is differentiable, and you can use this formula to compute tau point 1, which is the Hausdorff dimension of the measure. For q less than 0 of this, the result was the LQ spectrum was computed by Feng, Dejun Feng, for q less than 0, and he showed that tau q is not differentiable at 1 point. So for Bernoulli convolutions associated with Poisson numbers, Feng has computed the tau q for class of those measures. Okay. And the multifractal formalism was proved by Lau and myself concerning a class of self-similar measures that include all the Bernoulli convolutions associated with Poisson numbers, and Lau and Feng generalize the result. All right, so there's a lot of work concerning the multifractal formalism. It's still a very active research area. So finally, I want to talk about the analytic aspects of self-similar measures and how it's related to the LQ spectrum. So, so given a fractal set, we can get a self-similar measure supported on the set. Okay, but this measure will, definitely will affect the physical phenomena on this on the fractal set. Okay, so to describe physical phenomena, we'll construct a Laplacian related to the measure. Okay, so so this is a weak formalism to construct a Laplacian. There are Laplacian defined on the fractal. Okay, so by Kigami and by probability methods, this is a weaker one. We define a Laplacian on an open set containing the support of the measure, containing the fractal. Okay, But for infinite Bernoulli convolutions, the support is the whole interval. So this Laplacian is the correct Laplacian on the fractal. Okay, so the condition we need is that the lower L infinity dimension is greater than n minus 2. N is the dimension of space. Okay. So one can show that under this assumption, there exists a self-adjoint operator, which we call delta mu delusionally Laplacian on the support on the set on omega. Okay. And you can also one can also show that there exists an orthonormal basis of eigenfunctions. So the eigenvalue counting function n is the number of eigenvalues less than or equal to lambda. Okay. And the growth rate of the eigenvalue counting function is described by the spectral dimension, okay, ds, which is limit of the log of the eigenvalue counting function over log lambda as lambda tends to infinity. Okay, the number 2 here is not really needed. The reason that we put a 2 here is because in the classical Weil law, the eigenvalue counting function is like lambda to the n over 2. Okay, so that's why we put a 2 here. Right. So the spectral dimension plays an important role in studying analytic properties of the Laplacian. For example, if you want to study the wave equation on this interval supporting a fractal measure, then you study the Laplacian heat equation, etc. Okay, so the spectral dimension is used in studying problems like heat kernel estimates. Okay, so heat kernel estimates for fractals is different from heat kernel estimates for the regular Laplacian or Laplace Beltrami operator. One of the properties is sub-Gaussian heat kernel estimate. Okay, so and it shows that fractals, behaves quite differently. So in our research, we compute tau q and the spectral dimension separately. Okay, so we did a lot of work computing tau q, and then did a lot of work computing the LQ, the spectral dimension. I noticed that the formulas are, can be are related, but I was not able to prove that they're related. The result was the connection between spectral dimension and LQ spectrum was proved by Kasabirmer and Niemann in a preprint. Okay. So for a class of self-similar measures, including a class of measures including self-similar measures, they proved that the spectral dimension is 2 times Q star, where Q star is the unique solution of this equation. Tau Q star equals n minus 2 times Q star. Okay, so this is general formula for a class of measures. So it relates spectral dimension with LQ spectrum. So LQ spectrum encodes a lot of information about the measure and different areas of research concerning the measure. Okay, thank you. That's the end.
All right. Questions?
Could you please return to the slide with the spectral dimension?
Sure.
In principle, there is a well-known question posed by cats. Can one hear the shape of the drum? And this is related to Weil theorem, which tells how the integrated density of states is related to eigenvalues. I think that this is something similar to what are you doing, no?
Yes, I think it's similar. So the spectrum reflects the geometry, right? The spectrum reflects the geometry. But here, we want to see how the spectrum reflects the measure, the measure, the properties of the measure, because the geometry is the same.
But
Yeah.
can you hear the multifractality in looking at spectral properties of your system?
I don't think I can answer the question. So
The question can go. So this BS is just one parameter.
yeah, it's right, just one parameter. Yes.
Function.
All the eigenvalues of delta.
Right.
What does it tell you about
Yeah.
how the multifractal?
Yeah. That's what we want to do. Yeah, I wasn't trying to find out. Yes. No, it's not it's not well understood. Yes. So how the eigenvalues reflect the properties of the measures. So in the Weil law, there's a leading term. Okay, there is a leading term that has to do the volume of the set. So it's our methods do not give us even the leading term of in the Weil law. So we just get the dimension so far, not the the geometric or measure theoretic properties of measure. That's what we're trying to do. Yes.
You just mentioned that for complex spectral dimension means, what is the chance that running the motion on the fractal will come back to a small neighborhood with the fractal?
Right, because
Yeah.
the return probability gives you the density of states. Right?
Yeah.
Meaningful in several areas.
I would like, you mentioned that there are orthogonal states, there is orthogonal basis.
Yes.
Can they be computed explicitly, and what kind of functions appear?
Yes. For the simple one, the self measures like on 1 dimension or 2 dimension, we can compute them in the sense that we use finite element methods to approximate the solution, and we can prove that the approximate solutions by finite element methods actually converge the actual solution. But for general measures, we do not have like closed formulas for the eigenfunctions or eigenvalues.
But what functions do you approximate? Is it some
The eigenfunctions. We're going to approximate the eigenfunctions, eigenvalues by using finite element methods. Yeah, in 1 dimension and in 1 dimension. We also have in higher dimensions, but harder. But no, we don't have closed formulas for them.
So, more questions?
Yeah, sure.
The way the Hausdorff dimension is defined, if I understand it correctly, it can be any arbitrary real number, right?
S can be arbitrary any real number, but when S is greater than the dimensional space, the Hausdorff dimension will be 0.
Is there any particular situation, interesting situation, where Hausdorff dimension to be, let's say, rational number? The reason I'm asking is, as you know, there are some statistical mechanical systems where, let's say, self-avoiding random walk or percolation or, I don't know, Ising models, where some internal loop, internal path is actually this self-similar. And for them, there are conformal field theory description. And the central charge of this conformal field theory is by SLE formula related to Hausdorff dimensions. Now I'm wondering, is there a situation where the Hausdorff dimension is rational number, so it gives us rational conformal field theory, for example?
You can construct them, but I don't know. I think you can construct fractals with rational numbers, but I don't know anything that's particular or special or interesting about when the numbers, when the dimension is rational. Yuval, you?
Indeed, in the case of SLE theory, this is a special side of fractal geometry. There, really rational numbers come up naturally. Like the most famous is dimension of the Brownian frontier is 4/3, and dimension for SLE2, which is the limit of loop erased walk, is 5/4. So there are examples from that theory. But in this theory of self-similar sets, what replaces the rationals, as you saw in these examples, is actually instead of ratios of integers, ratios of logs of integers come in naturally. Like for the Cantor set, you have log 2 over log 3, and that is well, it's exponential, but not with base e, right? So so that is, those numbers play a role in, like, when you do b-adic expansions, and you saw them appear in some of these examples as similar.
There are examples where the fractal dimension is square root of something.
More questions? So this, in your LQ spectrum, what is R? What are those balls that you're adding? What is R in that definition?
Let me return to the slide.
Yeah, okay, that formula. LQ spectrum. Yeah, so what is, yeah, so what are you, this one.
Okay.
So what is XI? What is I?
Oh, Xi is
What
the
are you?
center of a countable collection of disjoint bars. These bars are centered in the support of the measure. Yes,
Okay,
so we try to pack the support by these delta bars.
I see.
Of the same size.
And then this measure mu, for instance, in this example where you had a self-similar set, and it was being generated by this P1, P2, P3. So
Yes.
this measure mu doesn't depend on the choice of generators?
Oh, it does.
It does.
It does. It does. It depends on the
so it's
the maps and also the weights they assign. Yeah, it does.
I see. And then another thing about this, what you called it, something like convolution. Infinite convolutions.
Yeah, infinite convolution.
Why did you choose that particular number for your?
Oh, yes. Yeah, good question. Yeah, the golden ratio.
Yeah, exactly.
Yes, for Poisson numbers. So first of all, Elders proved that mu r is singular if r is the reciprocal of a Poisson number. So we have a class of measures that are known to be singular. And if they're singular, their spectrum is LQ spectrum is not linear. It's interesting. Then we try to compute the LQ spectrum for these Poisson numbers, but we're not able to prove a formula like this except for this very special number, and we used a technique introduced by Strickhartz. It's called second order identities, and no other Poisson numbers seem to satisfy this property. So that's the only one we did. But De Junfeng used a different method, and he was able to compute LQ spectrum for a larger class. So and then a lot is unknown. But the Poisson numbers are the only class known to have a singular to give rise to the singular Bernoulli convolution. That's a lot of unknown. Yes.
I see. And there is just literally, you just found the golden ratio working for this thing, like
yes.
Just randomly. It's just very. That's how you find them. Yeah, good. Good. I see. Very nice. Okay, so a silly philosophical question for an algebraist, because I'm another planet with respect to you. Does Kakaya conjecture imply anything about LQ spectrums?
I do not know. I do not know.
Does it?
I would just mention to your question, so typically rational numbers emerge as confirmed dimensions.
Okay, good. But that's not the answer to my question. So does it or does it not? Does it?
I do not know. I do
I
not
see.
know.
Okay. More questions? Okay, let's thank the speaker again.